desert has been holding a secret locked away for millions of years, buried beneath ice kilometers thick. Imagine a landscape larger than Europe, entombed in frozen water, the Antarctic ice sheet, a monumental feature that shapes weather and sea levels worldwide. For centuries, explorers and scientists saw only its surface. All that time they were walking on a hidden world, above a secret network of rivers and lakes. Deep beneath the glaring white surface of Antarctica lies a world of perpetual. Here, hundreds of lakes are scattered across the continent, hidden from our view. These are the subglacial lakes, bodies of liquid water sealed off from the outside for an immense time. Some have been isolated for hundreds of thousands of years, others for millions. They are not small ponds either. The largest of them, Lake Vostok, is one of the biggest in Ontario. Vast sea oasis of ness in these buried worlds are unlike anything found on the surface of our planet. The pressure is immense, exerted by the 3 to 4 kilometers of ice pressing down from above. It is a weight so great it would crush a military submarine. And of course, there is the darkness. An absolute, unyielding blackness that has not been pierced by a single photon for geological ages. How does one find a lake hidden under 4 kilometers of solid ice? You cannot see it. You cannot simply walk to its shore. The discovery required a leap of imagination and technology. Scientists had to find a way to peer through the ice without physically touching what lay beneath. The primary tool is radar, ice-penetrating radar. Aircraft fly with these instruments over the ice. They send radar down through the waters until they hit a boundary, something different. Hitting bedrock produces one kind of bounce. Hitting liquid water smooth, very strong. Interpreting those ghostly echoes, scientists mapped a hidden liquid landscape. One echo at a time. The flat reflections revealed lakes. The flat reflections revealed entire river systems connecting them. Once a lake is found, the next challenge is how to reach it. Drilling through kilometers of ice requires surgical precision. The greatest fear is contamination. Of all the subglacial lakes, none has captured the imagination quite like Lake Vostok. Discovered in the station, it is the giant of this hidden realm. It is immense, stretching for 250 kilometers and reaching depths of over 8. Buried beneath nearly 4 kilometers of ice, it has been sealed off from the surface for an estimated 15 million years. It represents a lost world, a fragment of our planet's past preserved in a deep freeze. For years, it was the ultimate prize, a target for exploration, pushed the boundaries of science and technology. The challenge of reaching Lake Vostok was formidable. The Russian Antarctic program spent years carefully drilling down the lake's surface to analyze the ice cores extracted along. These ice cores themselves climate record, containing trapped air bubbles that tell the story of Earth's atmosphere over the past 400,000 years. The ice just above the lake, known as accretion ice, is even more special. When scientists finally analyzed this accretion ice, they found the first tantalizing hints of life. The evidence was microscopic, the chemical signatures, DNA fragments of bacteria. While Lake Vostok is the largest, other smaller lakes have proven just as revelatory. One such place is Lake Mercer, a subglacial lake in West Antarctica, about 1/10 the size of Vostok, lies beneath a more modest, though still immense, 1 kilometer of ice. In late 2018, a team of American scientists used a sterilized hot water drill, bored through the ice sheet, and lowered instruments into the dark water below. What they found was utterly unexpected. The team expected microbes, and they found them. The water was teeming with bacteria, at concentrations like the deep ocean. The scientists lowered cameras, sensors, and water samplers into the inky blackness, painting a picture of this unseen environment. The lake was active, water slowly circulating, a muddy bottom rich with minerals. The real shock came when they examined sediment samples. Tough shells of tiny crustaceans, preserved husks under the microscope, hardy bodies of tardigrades, water bears under magnification. The discovery of life in these buried lakes begs a fundamental question. How do they survive? On the surface of our planet, almost all life depends directly or indirectly on the sun. Plants use photosynthesis to convert sunlight into energy. Algae use photosynthesis to convert sunlight into energy, forming the base of the food chain. In a world of absolute darkness, photosynthesis is impossible. So what powers these hidden ecosystems? Life here are extremophiles, lovers of extreme conditions. The subglacial microbes are chemotrophs, chemical eaters. They derive energy from chemical reactions, not light. Microscopic miners, they eat minerals in rocks and sediment. They break down compounds of iron, manganese, and sulfur, releasing tiny sparks of energy, just enough to live and reproduce. A slow life. Imagine a night, a landscape or an endless icing. Inhabitants, ancient bacteria, archaea, some isolated for adaptations for immense pressure and near-freezing water, cellular machinery that runs much slower than to truly chemosynthesis. While the word may sound complex, the concept is beautifully simple. It is life's alternative to photosynthesis. Photosynthesis uses light energy to build organic matter from carbon dioxide and water. Chemosynthesis uses chemical energy. The microbes in these layers of this unique alchemy, turning inorganic minerals into the stuff of life. They are the producers in this dark food web, just as plants are the producers in our sunlit world. Think of it like a burning fire. Certain minerals contain chemical energy. Iron pyrite, fool's gold, compounds of salt. When these minerals react with other substances in the water, such as oxygen that might be trapped in the lake, that energy is released. The chemosynth evolved specialized enzyme tools that control and capture this. They use it to power their metabolism and to fix carbon, taking dioxide from the water and building it into the organic molecules they need to grow. This process is not entirely new to science. We first discovered chemosynthesis in the 1970s hydrothermal vents. There, mineral-rich water feeds communities supported by chemosynthetic bacteria. The discovery of a similar process at work under the Antarctic ice shows this is a fundamental strategy for life without light. Antarctic ice are more than just a scientific curiosity, of a completely. They force us to